तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, in today's class we shall begin our discussion on MOS logic circuits. Okay. So, we shall see how the MOS logic circuits developed from the initial stages to the present logic configuration. Okay. Now, if you take an MOS transistor, just what we had discussed last class. So, this is the symbol, say we of an n channel MOS transistor, okay, which we shall use. Okay. So, this is the source terminal, this is the gate, and this is the drain. All right. For a p channel MOS transistor, okay, what we are going to do is we are going to have a bubble here which indicates that it is a p channel MOSFET. Okay. So, you have a drain, you have a gate, and you have a source. All right. So, anyway, we shall come to the p channel MOSFET later on. Okay. For the time being, we shall be using only circuits which contain n channel MOS transistors. Okay. And we have already seen that the n channel MOS transistor, the current voltage relation is given by the drain current, okay, which is flowing here, ID is equal to 0 when V, the gate to source voltage, is less than what is called the threshold voltage VT, which is a very important parameter of the MOSFET, okay, is equal to K by 2 twice VGS minus VT into VDS minus VDS squared, okay, for VGS greater than VT and VDS less than VGS minus VT. Okay. So, this region of the characteristics is called the linear region of the characteristics, and when VDS becomes equal to VGS minus VT, okay. So, what happens is you have 2 VGS minus VT squared minus VGS minus VT squared. So, this becomes VGS minus VT squared. Okay. So, you have K by 2, okay, VGS minus VT whole squared for again VGS greater than VT and VDS greater than equal to VGS minus VT. All right. So, this the characteristic curve for this MOSFET is something like this. This is the drain current when you are plotting versus the drain to source voltage. Okay. You have the curves for different gate to source voltage. All right. So, this part of the characteristics to the left of this line, okay, this is the linear region, this is the linear region, okay, that is when VDS is less than VGS minus VT, okay, this equation. All right. So, you see that in this case the current increases with voltage, with drain to source voltage. All right. So, it is called the linear, it is almost a linear, it is not exactly linear, but it is almost a linear characteristics. Okay. That is why it is called a linear region of the characteristics. Okay. And this part of the characteristics, when the current is almost a constant, okay, and is independent of the drain to source voltage. It is called the saturation region of the characteristics. So, you must be careful when talking of the saturation region of the characteristics with relation to a bipolar transistor, okay, where this region is not the saturation region, this is the active region in a bipolar transistor. Okay. So, this is the saturation region of the characteristics, all right. Okay. There is one more thing, that in the saturation region the current is not exactly a constant, okay. There is a slight increase in the current, okay, which is due to channel length modulation, that is the effective channel length is reduced because of the penetration of the drain depletion layer. So, usually you have one more term in this, 1 plus lambda VDS, okay. 1 plus lambda VDS means that with drain to source voltage, okay, the current increases slightly, okay, all right, and this lambda is a quantity which is a small quantity, okay, much less than 1, okay. So, with the drain to source voltage there is a small increase in the drain current. Now, just to have a continuous curve, that is when you move from the linear to the saturation region, okay, that is there should not be a discontinuity in the drain current, okay, because that will give rise to lot of problems in simulation, okay. That is when the say along this line at this when you in this line, okay, this left side is linear, right side is saturation, okay, but at this point if you calculate the current using the linear relationship, okay, or the saturation relationship, the current should be the same, okay, all right. So, when VDS is equal to VGS minus VT, okay, the current should be the same irrespective of whether you are using the relation for the linear region or the saturation region, okay, otherwise you have a discontinuity in the curve. So, that is why, so if you have a 1 plus lambda VDS here, you also have to include a 1 plus lambda VDS in the linear region expression, okay, otherwise it will give rise to discontinuity, all right. So, that is why you also have a 1 plus lambda VDS, although it really is not quite it does not come from physical considerations, but from the circuit simulation point of view to avoid any discontinuity between these two regions, okay. But the point is this lambda VDS term is proportional to VDS. So, in the linear region VDS is quite small. So, this lambda VDS term is going to be quite small, and so the contribution of this term is going to be quite small, okay. Only when you go into the saturation region, okay, this term really has some effect. So, from that point of view it is not going to be very inaccurate, all right. So, this is the equations which are generally used, okay, for simple simulations, okay. Of course, there are other more complicated models also, which more exact models, okay, but for the sake of some hand calculations, okay, and trying to understand how the circuits work, okay, we shall use these particular equations, okay, to model the MOS transistor, okay, when we take up for discussion, all right. Okay. Now, this again when we take up the MOS digital circuits, we shall have to start with the inverter, which is the basic building block, okay, on any digital circuit, okay. So, how do you make a MOS inverter, okay, all right. Well, the most obvious and the simplest circuit which one can think of is having the MOSFET here, okay, the source is grounded, okay, and you have a resistance here, okay, the load resistance, supply voltage, and you have an input voltage here, and this is the output voltage, okay, all right. So, this is the circuit of a MOS inverter circuit, okay, this is an MOS inverter circuit, all right. Now, how do you obtain the input output characteristics? Okay. Again, as we have done in the case of a bipolar transistor, we go to the output characteristics of the MOSFET, okay, which is given here, and then what we have to do is we have to draw the load line. Okay. What is the load line? The load line is the current voltage characteristics of the load, okay, taking VDD as the origin, that is the supply voltage as the origin, and drawing it in the inverted fashion. Okay. So, something like this is the load line. Okay. So, here this intersects, so at VDD by RL, where L is the load, that is when I okay, that is this is the equation, all right. This equation is the load line equation is given by ID RL plus VDS is equal to VDD. Okay. Okay. So, when VDS is equal to 0, okay, ID is equal to VDD by RL, all right. So, it comes here, okay, and when ID is equal to 0, VDS is equal to VDD. Okay. So, these 2 points, it is the equation of a straight line, all right. So, this is the load line, okay, and as you know, so these are the these are the characteristics of the MOSFET for different gate voltages, okay, all right, and gate voltages is the same as the input voltage here. So, what happens when you increase the input voltage? Okay. So, the operating point is given by the intersection of the load line with the characteristic curve. Okay. So, when the input voltage is given by this value here corresponding to this curve, the point of intersection is here, okay, which means that for the MOSFET, okay, the drain to source voltage is this much, okay, and the drop across the load resistance is this much. So, together they make up VDD. Okay. All right. Now, when you go to the next curve, that is you have increased the input voltage, okay, the point of intersection is here, which means that again the drain to source voltage has reduced, okay, whereas the drop across the load resistance has increased, okay, and so on. As you go on increasing the input voltage, what happens is the drain to source voltage keeps on reducing, all right, and which means, and the drain to source voltage is the same as the output voltage of this circuit. So, as the drain to source voltage increases, the output voltage falls, okay, as the drain to source voltage reduces, output voltage falls, that is when the input voltage increases, the output voltage falls, which is what you expect in a inverter. Okay. So, if you just plot the exact input output characteristics, okay, so V in, V out. Okay. Now, when V in is 0 volts, what happens? Which is the characteristic curve here? We see, you see, if you look at these equations here, ID is equal to 0 when VGS is less than VT. Okay. So, if VT say is 1 volt say, so when V in is less than 1 volt, okay, ID is 0, that is the drain current curve corresponds to, is over the x is corresponds to the x axis here. So, the point of intersection is at VDD. Okay. So, up to V in is equal to VT, okay, the output voltage is going to be equal to VDD, all right. So, you have this up to VT, input VT, output voltage is equal to VDD, and then what happens? As you go on increasing the input voltage above VT, okay, the output voltage keeps falling, all right. So, the input output characteristic is going to be something like this, all right. So, the input output characteristics, it falls like this, okay. Now, so in this part of the characteristics, okay, the circuit here actually, all right, this behaves as an amplifier, all right, that is and the gain of the circuit is, of course, the gain is negative, that is when the input increases the output falls. Okay. If the gain of the circuit is made higher, all right. It would mean that the output, the fall would be sharper, okay. That is, if the gain is increased, no, it will be something like this, okay. So this way it is for larger gain, okay. Now, so if you want to have a better characteristics, okay, we have to increase the gain, okay. Now, what is the gain equal to? Gain we shall say is equal to d V out by d V in, okay, and V out is equal to VDD minus IDRL, all right. So what you get is minus DID dV in into RL, okay. And what is this ID DID dV in? GM. So it is equal to minus GM into RL, okay. So if you have if you want to have a higher gain, okay, one way would be to increase the load resistance, okay. So if you increase the load resistance, what happens to this load line, okay? The load line is going to be something like this, okay. That is, if the load resistance is higher, okay, the load line is going to be something like this, okay. That is the lower curve here, okay, this curve, all right. The slope is going to be higher, okay. This is because this point is VDD by RL, all right. Now, so you see that if, well, it is clear from here that if the load resistance is increased, then the current, okay, flowing through the device is going to be less, isn't it? Because the operating point, okay, at the operating points the current would be less, okay. Okay. Now, it is quite obvious also if you see from this relationship, okay. Now, if you look at this curve, if you look at this characteristic equation, okay, it is quite obvious that it is obvious that the GM of the MOSFET is higher in the saturation region, all right. The currents are higher, okay. That is the difference, basically GM is del ID del VG. So how much does the current change with VG? So if you look here in the linear region, okay, if you look at the different curves with VG, they are more closely packed, okay, whereas here they are more widely separated, all right. So the device has a higher GM, okay, that is del ID del VG for in the saturation region, okay, that is clear. And if you look at this expression for the saturation region, okay, what is del ID del VG? Okay, it is proportional to if you just differentiate this with respect to VGS, okay, you get K VGS minus VT, okay. GM is equal to K VGS minus VT, okay, which means that GM depends on VGS. So larger the gate to source voltage, larger is GM, okay, the transconductance, all right. It is also quite obvious that in fact if you have the same difference, if you plot the output characteristics with equal increments of VG, okay, the curves will be more and more separated, okay, if you go for higher and higher gate voltages, okay, because the GM increases with VG, okay. At lower gate voltages the GM is less. So now if you look at this equation, there is a problem that if you want to increase the gain, you have to increase RL, but if you increase RL, you will be operating at lower current levels, okay, which means that you have lower GM, okay, all right. So that is a problem, okay, which of course with this circuit we cannot avoid, okay, all right. So anyway, you get a characteristic like this, but so this was, well, the simplest of the inverter circuits one can think of. But again, as we know that in integrated circuit, okay, fabricating a resistance is a problem, okay, especially if you want to go for high values of load resistance, okay, it is not advisable, okay. So the next it is better if you can use an active device, okay, as a load, okay. So or an active device here in a MOS circuit, MOS based circuit would be a MOSFET, okay. So obviously, okay, the people went for a MOS transistor as the load device, okay. So the first circuit which was used was the load, what is called a saturated load, okay. That is, the circuit configuration is something like this, okay. So this is our MOS transistor, okay, here, and for the load you have another MOS transistor with the gate to drain shorted, okay. So this is VDD, okay. So this acts as the load device, okay. The gate to drain is shorted. So what does it mean if the gate to drain is shorted? It means VDS is equal to VGS, okay. The drain to source voltage is equal to gate to source voltage, and we have already seen that the transistor goes into the saturation region when the drain to source voltage is greater than VGS minus VT, and if the drain to source voltage is equal to gate to source voltage, then obviously, okay, drain to source voltage will always be greater than gate to source VGS minus VT, which means that this particular transistor would always be in saturation, okay. So if this is the load device, now what is going to be the output characteristics? Again we follow the same procedure, okay. We draw the output characteristics of the MOS transistor, okay. I think that's enough, all right. And then we have to draw the load line, okay. For the load line, again we have to draw the characteristic of this device, okay, again with VDD as the origin here, okay, starting from VDD as the origin, okay, and just inverted like this, okay. Now what is this characteristics of this device? How does it look like? Okay, since this is a saturated transistor, okay, we have to take the expression for the saturated case, okay, which is this one, that is k by 2 VGS minus VT squared, okay. And so VGS, see, VGS is actually equal to VDS for that, okay. So that is the voltage across the device. Basically it behaves as a two terminal device because you are shorting the gate and the drain, okay. So it is this equation, it is a square law type of relationship, okay. But one important point here is that it is k by 2 VGS minus VT whole squared. So what happens when VGS is less than VT? Current is 0, okay. This current is going to flow only when VGS is greater than VT, okay, for this device. So when VGS is less than VT, there is current is 0, okay. So if you look at the characteristic, okay, for that I just want to draw it separately. This goes to this 0 up to VT, all right. So if you want to plot the IV characteristics of the load device, it is up to VT is 0 and then it follows a square law type of relationship, okay, all right. So now if you want to draw that, this use this characteristic as the load line in this curve here, okay, you have to draw it like this up to VDD minus VT, it is like this and then goes like this, all right. So, this is the load line, okay, all right. Now, so if you have this as a load line, what is going to be the output input output characteristics? Okay, we will draw it here. Okay, this is V in and this is V out. Okay, again the same question, when V in is equal to 0, okay, what is V out? Okay, when V in is equal to 0, the characteristic equation for the MOS transistor, anyway, see in this case when you have two transistors here, okay, the name given to this transistor, this transistor which is the lower transistor is called the driver transistor, okay, and this is called the load transistor, okay, all right. So, I mean just to differentiate which transistor we are talking of. Okay. So, this is the characteristic of the driver transistor when VGS is equal to 0 or V in is equal to 0 for the circuit, okay, this is here. Now, so where does the two characteristic, that is the load line and this characteristic, intersect? So, it intersects, it intersects all along this, okay. So, what is going to be the output voltage, whether it is going to be VDD or VDD minus VT or somewhere in between, okay, that is the question, all right. Now, what happens is when you want to discuss that, I think what we should bring out is that usually, okay, when we have not brought any capacitance into picture as such, because we are just drawing the static characteristics, but usually these devices will have a capacitive load, okay, which may be the input capacitance of the next device, okay. Now, what happens is when the input voltage goes from high to low, say, okay, so that this particular device, the driver device, is cut off, okay, that is basically the input voltage is less than VT. So, the driver transistor is off, okay. What is going to happen is the capacitance will be charged by the load device, okay, the load device is on, the output voltage was low. So, the output voltage is going to rise, okay, because the current will flow this way to charge the capacitance, okay. And as the output voltage rises, the source voltage of this load device, it is increasing and the gate to source voltage is falling, because the gate voltage is fixed at VDD, okay. And so, it up to what value can the output voltage rise? It can only rise till VDD minus VT, okay, because when the output voltage goes to VDD minus VT, okay, the gate to source voltage of the load transistor becomes equal to VT, okay, and then the current which is the load which is being provided by the load device to charge the capacitance goes to 0. So, the capacitance, the voltage across the capacitance cannot rise any further, all right. So, the output voltage of this type of configuration, okay, is going to be equal to VDD minus VT. It can never go beyond or above VDD minus VT, because if it has to go above VDD minus VT, the current has to be provided by the load device, which it cannot do when the source voltage goes beyond VDD minus VT, all right. So, the output voltage is actually VDD minus VT, all right. So, this is the output voltage, VDD minus VT, all right. And then of course, the situation is quite similar to the load device, to the the inverter with a resistance load, okay. You have, it is not really a straight line, but it is, okay, quite similar, the output voltage will keep falling as you go on increasing the gate voltage or the input voltage, all right. So, you have a situation like this, okay. So, this is VT, okay, So, after Vt the output voltage keeps falling. Okay. Now, again if you want to increase the slope or the gain of this inverter, what you have to do is you have to have a characteristic, okay, something like this, all right. That is, if you have a characteristic like this, see for the same gate voltage here, say if you take the same gate voltage, okay, that is the input voltage is somewhere here. So, it starts falling from V in is equal to Vt, but for the same input voltage here the output has fallen to a lower value, okay, for the same input voltage. For this, if the load line was this, if the load line is like this, it is still at a higher value. So, obviously if for this curve, okay, the gain is more, all right. Okay. Now, what does this mean? This curve, okay, for this curve, what is the difference between these two curves? These are the curves of the load device. What can you say about the transconductance parameter of the load device? This one, the transconductance parameter is less, okay, all right. So, this is the transconductance parameter is less, okay. Now, again if you consider, okay, that suppose if you consider that this is the load device, okay, and for the driver if you have a device with a larger transconductance, okay, that is, you know, all the curves is going to move up, okay, for the same V in the curve is going to move up, okay. That is, say for example if you consider this curve 1, okay, and another curve 1 prime, say, okay, they have they are for the same gate voltage, input voltage, all right, but with two different transconductances of the driver transistor, okay. So, this obviously has a higher transconductance, all right. So, if you have a higher transconductance for the driver transistor, the gain is more, all right, okay. And if you have a higher transconductance for the load transistor, the gain is less, okay. So, the gain actually depends on what is called the Kd by KL ratio, okay, where Kd is the transconductance of the driver transistor, all right, and KL is the transconductance of the load transistor, okay, all right. So, this Kd by KL ratio, so if you increase the Kd by KL ratio, then the gain is going to go up, okay. So, we shall come to that how it depends on that. I think we shall not we shall discuss that for maybe other logic circuits, but basically it is understood that if you increase Kd by KL ratio, all right, the gain goes up, okay. So, if you have increasing Kd by KL ratio, the gain goes up. So, in fact if you have similar devices, if you consider them to be similar devices, that is they are fabricated simultaneously, all right, then what does this Kd and KL depend on? It depends on the width to length ratio of the individual devices, okay. So, you can control the gain by changing the sizes of the devices, okay. That is how it is usually done, okay. To change the gain, you control the sizes of the individual devices, that what is called the W by L ratios of the individual devices, okay. It is clear. So, we shall come to how exactly it depends maybe for some more other circuit, because well this circuit, okay, well it did not last in the sense that it was replaced by more by better circuits, okay. So, this is the circuit, this is the output characteristics of this particular circuit. Obviously, this has a disadvantage in the sense that the output voltage does not go up to VDD. Okay, all right. You are losing a voltage, output voltage. The logic swing is less than the other circuits by Vt. Okay, and this has repercussions in the sense that the logic swing less means the noise margin is less. Also, the speed of the device is going to be less, in the sense that since it is not going all the way to VDD. Say for example, you know, when the output voltage charges to VDD, if you have a circuit with output voltage charges to VDD, so it is output voltage goes up like this, okay, and if the output voltage charges to VDD minus VT, now it will go up like this, okay. So if you say that the logic threshold is somewhere here, you know, where above which you are going to say it is logic 1, okay. So obviously if it is charging towards VDD minus VT, so this is with time how it charges output voltage, okay. So the one which is charging towards VDD minus VT is going to take more time, all right, it's quite obvious, okay. If you are, if this is the value, okay, logic threshold, say, which you consider as the threshold between 0 and 1, okay. So these are the some of the problems. So one has to see how to remove this problem. So the next circuit which was contemplated or used maybe was the one with not a saturated load but with a linear load, okay. That is, you use the load device in such a way, configure the load device in such a way that it is not in the saturation region but in the linear region of operation, okay. So how do you do it? I just, so you have a okay, actually it is load operating in the linear region, okay. So what you do is you have this gate voltage, you have a separate power supply for the gate voltage, okay, VGG, okay, and if VGG is greater than VDD by VT, okay, that is VGG minus VDD is greater than VT, all right. That is, what you are going to have is that, see, this transistor, the gate to source voltage is always going to be greater than the drain to source voltage by more than VT, okay. So VDS is always going to be less than VGS minus VT, okay, all right. The drain, the gate voltage, gate to source voltage is greater than the drain to source voltage by more than VT, because VGG is greater than VDD by more than VT. So VDS will always be less than VGS minus VT, okay, which means that the transistor is always going to be in the linear region of operation, okay. And this transistor is always going to be on because this is greater than VDD minus greater than VDD by VT, and the maximum value which you can have here at the source point is VDD, all right. And so since VGG is greater than VDD by more than VT, so VGG minus this source voltage, which can be maximum VDD, okay, the gate to source voltage of this device is always going to be greater than VT. So this transistor is always going to be on, okay. So if you look at the load line for this, okay, if I may draw it here again on the same characteristics, okay, for the linear load, okay, it is going to be something like this, all right. So this is the linear, Okay. All right. So, which would mean that it is from the performance point of view, the input output characteristics point of view, okay, the output voltage would go all the way up to VDD. Okay. When Vin is 0, the point of intersection is here, all right, up to Vin is equal to Vt. So, if you look at the characteristics, okay, the input output characteristics, okay, so this is V in, this is V out. It is going to be similar to the one with the resistive load, okay, it goes all the way like this. So, up to Vt it is VDD, okay, and after that it keeps falling, all right. So, it is similar to the VDD, it is in fact better than the saturated load, but there is a problem, okay. The problem is that you have to you must have two power supplies, okay, one for the drain and one for the gate, okay, which is not very good thing to have, because you will unnecessarily increase the cost of the system, because you have to have two power supplies, you have to have more interconnections, because again you have to take out two power supplies, okay, and that creates a lot of problems. So, from that point of view, okay, it is not a good thing, okay, having two power supplies. So, we should again try to eliminate it, okay. So, how to do it? So, the next type of inverter which came was with a different type of device altogether, okay, which is called I shall come here, this particular device is called a depletion it is called a depletion mode load, okay. Okay. Now, all the transistor characteristics or the devices which we have been discussing now come under the category of enhancement mode devices, okay. That is, the threshold voltage of such a device is positive, okay, greater than 0, and at V in or Vg greater Vg equal to 0, the device is off, it does not conduct, okay. That is, Id is equal to 0 when Vgs is less than Vt, okay, that when Vt is positive, okay. So, it is a normally off device, okay. The difference with a depletion mode load is that it is a normally on device, that when Vgs is equal to 0, the transistor conducts, and in fact you have to apply a negative voltage to switch it off, okay. So, the construction of the device or the cross sectional view of the device is something like this. Well, in a normal n channel MOSFET you have the structure like this, as we have seen already. So, this is the oxide, this is the metal. So, you have the MOS structure, this is the N source. So, this is the source, this is the gate, this is the drain, all right. So, you have to apply a positive gate voltage to create the channel, okay, that is the channel consisting of electrons, okay. Now, here in a depletion mode transistor, what you do is you already create a channel, that is you use ion implantation to create an N channel here, okay. That is, this region is already doped N type at the surface, okay. So, when you apply a drain to drain voltage, when the gate voltage is 0, say, when you apply a drain voltage, there is a current flowing, this behaves as a resistance, okay. Now, what you have to do is and if you go on increasing the gate voltage above 0, okay, well, you have a larger concentration of electrons, Okay. If you have positive here, you introduce, okay, and the current goes on increasing, just like in the case of an enhanced type device. But what you do is, when you apply negative gate voltage, okay, when the gate voltage is negative here, you should induce positive charges, okay, in the semiconductor. How do you do? What happens really is, the electrons from the surface, okay, they get repelled from the surface. Okay. So, if you apply a negative voltage here, okay, positive charges will be, it is like a capacitance. Okay. So, you should have positive charges in the other plate. Okay, that is, the electrons get repelled from their surface here, and you create what is called a depletion layer. Okay, and the depletion layer thickness will go on increasing as you go on increasing the as you make the gate more and more negative. So, at a particular gate voltage, negative gate voltage called the pinch off voltage, okay, the channel will be pinched off when the depletion layer covers the entire channel, okay, and the current goes to 0. Okay. So, you have instead, just like you have a threshold voltage for n channel device, enhancement type device, here you have what is called a pinch off voltage. Okay, that is given by the symbol Vp. Okay, Vp is the pinch off voltage. All right. Now, so, and again, so basically what happens is, if you go on increasing the negative voltage, okay, the depletion region increases and it goes like this. All right. Now, also when you are, suppose if you have a gate voltage of 0 volts, okay, what is happening is, and you are applying a drain voltage, a positive drain voltage. Okay. As you are increasing the positive drain voltage at the drain end of the channel, so this is becoming more and more positive. So, what about the gate to drain channel voltage? It is becoming more and more negative. The gate is becoming more and more negative with respect to the channel. Okay. So, again, what happens is, if you go on increasing the drain voltage up to a particular value, okay, that is basically the gate to channel voltage at the drain end, when it becomes equal to the pinch off voltage, okay, the channel is pinched off. Okay, the depletion region keeps widening at the drain end, okay, and the channel gets pinched off. Okay, and that is why you have a saturation of current, just like you have in the enhancement type devices. Okay. So, basically, all right, in order to model this depletion type device, we use the same set of relations. Okay. We have the same set of relations because it is almost identical, okay, except for the fact that instead of threshold voltage, here you have a pinch off voltage, and this pinch off voltage is going to be negative. Okay, that is, if you look at this equation here, that ID is equal to be 0 when VGS is less than the pinch off voltage, which is negative. Okay, that is, it is more negative than the pinch off voltage, then the current is 0. Okay, and when the gate to source voltage is less negative compared to the pinch off voltage, you have a channel. Okay, all right. And so, it is a similar type of relations, only that, I mean, you can think of it in such a way that the threshold voltage, okay, is not positive, but just negative number. Okay, and then it behaves in a similar fashion. Okay, so that is what is a depletion type device. Okay, and this depletion type device, we shall see, depletion mode load device, okay, gives a much better characteristics compared to all the load devices which we have talked of so far. Okay, and in fact, for a long time, a lot of circuits were fabricated using the depletion mode load, okay, till I mean the CMOS actually took over. In fact, the early microprocessors like 8085, okay, they were fabricated using the nMOS logic, okay, with a depletion mode load. Okay. So, we shall take that up next class.